Great. So we've learned about how two ways to do a 3D camera model. We can do just point anywhere or synthetic, but the problem with our standard synthetic model that I just showed you is it's not easy to make it look where we want to look. So what I'm going to do is I'm going to show you a variant on this, which I call the free look camera model, which is actually kind of the same thing. So it's actually not hard to do, but you approach the problem slightly differently so you have more flexibility. So imagine you have your scene. This is your coordinate system. This is 3D. This is your Y. This is my X. This is my Z, right? And going negative into the screen because it's right-handed system. Okay, great. Now imagine I have objects all over my space, right? That's supposed to be it doesn't really matter. I have these objects sitting around everywhere. Now what I would like to do is, let's say I want to look at that. I'm going to put my camera up here. Okay? It's kind of looking down and looking at that. I have a point here that I want to look at. And I want to have my camera centered on that point. This is the approach that we want to do. So let me explain how that works. One, we choose a camera position in the world, just like before. Okay, so that's going to be this point right there. Camera position in world coordinates. Okay, great. So we have that camera position in world coordinates. Two, let's choose the point in the world that we want to look at. Okay, we've already gotten that point right there. Great, so that's the point in the world that I want to look at. Then I can calculate my vector, that look at vector here. I can calculate that vector. That should be blue. It's easy. My look at vector is equal to point, that look at point right there, minus camera position. This is my look at point, right? That's a vector. Point minus my camera position. Great. That gives me that look at vector. While I'm at it, let's just dot normalize. So I have this vector here. Yay! So now I have a look at vector, which points at the direction of where I want to look. Now this is the next part is the part that seems to confuse people the most. I want to choose my up vector. Just like in the 2D model, except now I'm going to say, well, it's my rough up vector. And for example, I might just choose up like that. Okay, let's call it up prime. It's my rough up vector. Okay, I'm going to choose it roughly. And the reason I choose it roughly is because it needs to be orthogonal to my look at. And for you to sit down and figure that out, it's annoying. And so we'll get to that. For now, what general direction do I want it in? Typically, people choose x of 0, y of 1, and z of 0 straight up, okay? Let me show you why in visual, why that is. In the 2D model, I have my camera like this. And here's my up vector, and here's my look vector, and they're orthogonal, right? They're orthogonal. But if my camera's looking somewhere else, yeah, I want to make sure it's orthogonal. It's not as simple in 3D to go, yeah, just minus the x and plus the y, whatever. In 2D, we have a formula. It's a little trickier in 3D. So what we typically do instead is we just pick an up vector which is generally where we want it to be, okay? Because the up will eventually depend on the look direction. Right? I want my up to be there. But we'll get there. So we pick that rough up vector. Okay? Right. Let's walk away from that for now. We have look at, we have a rough up vector. Now point 4 is we can calculate. So remember, to make a basis, we're going to need 3 vectors, right? We're going to need 3 vectors that are orthogonal. So I'm going to add now to my picture, I'm going to add a new vector called side. And this is, you have up, you have look at, and side goes out the side. Imagine a handle, okay, on your camera. You're grabbing the handle of the camera to rotate. So we need this side vector. But luckily we can get it. I can calculate side, the side vector that I need that points out sideways from my camera. I can calculate side equals my look vector that I just calculated, look at, cross product with up. Okay, look at, up. It's a right-handed rule, and it's going to point out the side. Look at, up, it's going to point out the right side. So I'll calculate side being my look at, cross product, up, and side now is guaranteed to be orthogonal to both. Okay? So if I just try to draw that out, see if I can get this to work. This is I'm trying to draw a 3D camera. Artist, I am not. So here's my 3D camera, and it's looking somewhere over. My lens is backwards. Okay. And come on, you gotta be kidding me. Yeah, lens is out there. So it's looking that direction. That's look. Now we have this up, but now we need this coming out the side of the camera. So we need these 3 orthogonal vectors. And we can calculate that side by taking our rough up vector and cross-prodding it with our look, and now side is guaranteed to be orthogonal to both. So if I draw it out a little differently, right now we have side is orthogonal to look, and side is also orthogonal to up, but we don't know if up is orthogonal to look yet. And so that what we do is we recalculate up. We go, okay, now let's fix this problem that Jim mentioned where up and look might not be orthogonal, right? Actual look might be up or down, while up is here. So we can just simply do that. It's kind of like, it's not hard. Recalculate up as side cross product L. Side cross product L gives me straight up. Okay, great. And then make sure everything's normal the whole way. A unit length. You know, if you have 2 unit length, it'll be unit length, but make sure the whole way that it's unit length, okay? So just make sure that's done. So if we have that, so now we have up, which is, I'm going to go back here and put a prime note on there to indicate rough, right? So these are our rough vectors. There we go. And now we've actually come up with 3 orthogonal vectors. We have our look at that we've come up with. We now have a side that's orthogonal and an up that's orthogonal. So we're good to go. I want to comment this up thing. This part confuses people, the fact that, you know, I'm going to recalculate a new up, but it's not exactly where I pointed. But what we can guarantee is that up will stay within the plane. Defined by up prime, that's the rough up, and look at. Okay, so if I'm like this, you know, you can't see me very well. Let's try it with my fingers. If I'm like not orthogonal, realize that any 2 vectors always make a plane that connects them. So the new up will be in the same plane that you depicted, it'll just be orthogonal. It'll be close by. So it'll stay in that plane. So now we have three vectors, we can make a basis function. So the basis looks like this. Basis to go from camera space to world. We put in, let's just write this out. This is the x component of my basis. They call it u, v, and w, but we get confused. This is my y and my z component. So the x vector is my x-axis, which is my side vector, right? So my forward is the z, my up is my y, and the side is my x vector. So I put my side x there, side y, side z, 0. My y vector is straight up. That's my new up. That's not the rough up. It's the one that I've calculated. Up y, up z, 0. My z is my look at. Look x, look y, look z, 0, and of homogeneous coordinates like that. So one thing we want to do here, I'm going to put this in red to highlight it. We actually put minus signs in front of that z because people don't like thinking in negative vectors. So the whole calculations we've been pointing at the look at. Everything's pointing at the look at. But that'll give us a positive magnitude. Of course, all vectors have positive magnitude. But it'll give us a vector pointing in that direction, and the resulting basis will make z get bigger in that direction. We want to be looking down the negative z-axis to keep in a right-handed system. So I've been calculating everything actually is left-handed. I'm looking down this vector. And so to keep it in a right-handed system, I just put those minus signs in there, okay? I just put those minus signs in there just to keep it a right-handed system. Now you can also do that by rethinking the order of your cross products above and how you create your vectors. You can redo it and just make sure everything points in the right direction. It turns out that it seems to be more confusing that way. It's better just to work in the intuition of like I'm pointing here and I'm doing this, and then it's better to work that way and then just put the minus signs in here at the end when you're done, okay? So that's my advice. And that's what you'll find happen if you look in textbooks or online too. So that's, and of course now I have a point in camera space. I can transform it by this basis function. I'll put a b up here. And then I want to move my camera, and that's just like in 2D, so that's not bad at all. It's camera x, camera y, camera z, and then 1 for my other coordinate, 1, 0, 0, 0, 1, 0. Right? This is my t. So then, if I transform the basis, I'm in camera space, I apply the basis, I find out, I offset to where my camera is supposed to be, I'm going to get my point in world space. And because it catches people, I'm going to make this, again, make sure S, U, L are length 1. Okay? Make sure, otherwise it won't work. You'll add a scale factor in that you didn't mean to. Okay, so maybe I should say that too. So you move to camera coordinate system, then so 1, 2, right? Because it's backwards. Move to camera location. Great. So that's that. That's my basis to go from camera space to world. Now, of course, we typically want to go in the other direction from world to camera. So to go from world to camera, we just do all the inverses. So if I look at my thing above, I have a point in world space. Now t happened last, so I got to put t inverse first. And then B happened first, so I'll put B inverse last, like that. Remember that all that we do then, to invert the orthogonal matrix, we can just use the transpose. U, X, U, Y, U, Z, and then look X. look Y, look Z, and of course I'm gonna make it red, just make sure they're not missed. 3 minus points, 0, 0, 0, 1. Like that. And then to invert the translation, it's just using negatives for the movement minus CX. There. We're done. So this is great. This will transform from world coordinates into camera space, which is basically what you want to be doing in your pipeline. The last thing I'll mention is in the 2D model, we talked about zoom. What about zoom? Well, you can do it here too. You can add a scale in. It'll still do the same kind of thing, but it's typically not how it's done. Because it becomes unintuitive when you have perspective. So, if you're using perspective, how do you zoom in? Just move towards the camera. Right, just move the camera along the look vector or the negative look vector, and you can do it on the spot that you want to zoom in on. It's typically what's done. You can use the scale, and you'll get more of a modification of the field of view, and like maybe like a real camera, and that's something you can play with. But typically, if you want to go in, you just move the camera forward. That's how it's done. Now, you don't actually typically set up these matrices yourself. There's code to do it for you. For example, you can look at GL lookat is a standard GL command which creates this matrix using exactly the process I just showed you. It's not hard. In processing, it's called, the camera function. You can call that to set it up. And both of these, they take 3 parameters. They take the camera location. They take the lookat point. And they take your rough up vector. And with that 3 information, then we can calculate our basis. That's all we need. Cool. So that's how we do a synthetic camera in 3D. It's not hard.